Hello and welcome to this FP3 exam paper walkthrough. This was the January 2022 paper. You were allowed the formula booklet and a calculator. Question number 1. Use the definitions of hyperbolic functions in terms of exponentials to prove that this thing is true, where p and q are constants to be determined. Here we are going to start with the left-hand side, with the definition of cosh x in terms of its exponentials, e to the x plus e to the minus x over 2. We're going to substitute that in, expand out the power 4 bracket, and hopefully it will give us some terms that we want. That's 8 times e to the x plus e to the minus x over 2 to the power of 4, and the power 4 goes on the 2 as well, that's 16, so 8 over 16, and then e to the x plus e to the minus x power 4, and we're just going to expand that as we normally would, 1 over 2 lots of e to the 4x. Applying the binomial theorem as we go here, we've got 4e to the 3x times e to the minus x. The next in Pascal's triangle on the 4th row is a 6, and then it's 2 of these and 2 of these. Then we go back to 4, and it's 1 of these and 3 of these, and then we're back to 1, and it's 4 of these and none of the others. Now we can combine in each term. That's 4 to the x, and this is 4e to the 2x plus 6 plus 4e to the minus 2x plus e to the minus 4x, missed an x. Now we can group them. We've got 4x and minus 4x, and everything is over 2 here, so I'll make it look like the cosh definitions. We've got e to the 4x plus e to the minus 4x over 2, plus 4 lots of e to the 2x and 4 lots of e to the minus 2x. Again, over 2, because that's part of our cosh definition, rather than cancelling with the 4. And then we've got plus 6, and that's over 2 as well, so that's plus 3. Now my two sets of brackets here, they simply change into cosh 4x, 4 lots of cosh 2x plus 3. So comparing that to what we were given, p is equal to 4 and q is equal to 3. That's part A finished. Part B, hence or otherwise, so either using what you've done or in any other way that you like, solve the equation this. Now immediately I think to myself, it's a shame those two numbers don't match the p and q that I've got. That would be very easy. But we can kind of manipulate this equation so that it matches on the left hand side. The thing that we've just found is equal to 8 cosh power 4x, and then we'll see whatever is on the right hand side to make that true. So what we've got in part B at the moment is cosh 4x minus 17 cosh 2x plus 9, and on the right hand side 0. So if I want this to be a plus 4 cosh 2x and a plus 3, what I needed to do on the left hand side, I need to do on the right hand side to make sure this is still the same equation, is to add 21 cosh 2x and subtract 6. And the cosh 4x was already how we wanted it. So if you rearrange this equation, you get the equation one step above, but the reason for doing this is so that this left-hand side now matches exactly what we had in part A, and I can change that into 8 cosh power 4x, because that's the thing that we proved it was equal to in part A. Now if you wanted to just go back to exponential definitions and throw that in, that's fine. It did say or otherwise, so you could do this in any way you like. And you might think, well, how is this any easier? We've got a power 4 with an x, and then a power 1 but with a 2x. But remember, we can apply our double angle formulae with hyperbolic trig just as we can with normal trig. We have cosh 2x is equal to 2 cosh squared x minus 1. And if you forget that, there is enough information in the formula booklet to work it out. Here in the FP3 section, if you take this and you rearrange it for sine squared x and you substitute it in here, then you can use the double angle formula given here So if we substitute that in, that gives us 8 cosh power 4x is equal to 21 lots of 2 cosh squared x minus 1 minus 6. And now I have a quadratic in cosh squared x. 8 cosh power 4x minus 42 cosh squared x plus 21 plus the 6, 27. Can we factorize? Remember, if you don't like to factorize, or if it's not immediately obvious, you could just do the formula. But I think we need a 9 and a 3. Is that going to work? Yes, 36 and 6, so 4 cosh squared x minus 3, 2 cosh squared x minus 9. That gives us cosh squared x is 9 over 2, or cosh squared x is 3 over 4. Cosh x plus or minus root 3 over 4, which is a problem. I'll come back to that in just a second. Plus or minus 9 over 2. So the problem we've got here is that cosh x must be greater than 1, and this is less than 1. Therefore we're going to reject that and just work with this one. So x is equal to plus or minus r cosh root 9 over 2, realizing that we're also rejecting this negative symbol here. So inside that is just the positive root, but we do have the plus minus because when you do the inverse cosh of a number, you've got two options because of the symmetry of the graph. Looks something kind of like that. So root 9 over 2, wherever that is, has this root here, and this one here. Back to the formula booklet, you can see that caveat is written here to remind you, and also the logarithmic version of r cosh x, which is what we need here. So here it is down here underneath the graph, and I'm going to apply that with x is equal to root 9 over 2, which I could probably change into 3 root 2 over 2, slightly better form perhaps. So x is equal to 3 root 2 over 2 plus or minus, and that does come in there, the root of this thing squared, so that's just 9 over 2 minus 1. That's a 7 over 2, so we've got plus minus root 7 over 2, which is the same as root 14 over 2, so I can combine those fractions. We get 3 root 2 plus or minus root 14 over 2, and for some reason I have forgotten that it all goes inside a log. There we go. And there are our two answers. On to question 2. Figure 1 shows a sketch of the curve C with parametric equations. The curve C is rotated through 2 pi radians about the x-axis, so it's going this way, and is used to form a solid of revolution S. Using calculus, show that the total surface area of S is given by this, where P and Q are integers to be determined. 8 marks. Question 2, 8 marks, wow. Okay. Total here is in bold because a thing that no doubt lots of people in an exam situation will forget to do at the end of the question is to realize that the solid has a top circle and a base circle, as well as the curved surface area that we'll get from our formula in the formula booklet. So to try and avoid that mistake, even having realized right now, I'm going to do those 2 bits first, and then we'll come back to the middle section, which is the integral. To do this, I need to know the radius, i.e. the y-coordinate at this point, and the y-coordinate at this point. To double check I've got them the right way round, I've put 0 into this expression for x, and that gives me 0, so 0 in this expression for y gives me a 1, which tells me that this value here is a 1, so a1 is pi r squared is just pi. For the other one then, pi by 4 gives me an answer of root 2 over 2. That's this value here, root 2 over 2. So a3 is pi r squared is equal to pi by 2. So those are my base and top of the solid, Now we need our usual integration formula found in the formula booklet, and then add all three together. So going over to the formula booklet, here we have the formula for the surface area of revolution. We are doing it about the x-axis, so this is the correct formula, and we're using the parametric form. So it's this one here. So I've taken that from the formula booklet. The only thing I've changed is instead of t, our parameter is theta. We're going from 0 to pi by 4. So now I need to work out the bits that will go in the square root. So if x is log secant theta plus tan theta minus sine theta, then dx by d theta, I'm going to jump back to the formula booklet because differentiating that log makes me think there might be a standard derivative. It kind of is, but it's not in the differentiation section. It's in the integration section of the P4 part of the formula booklet here. So if you integrate secant x to get this, then differentiating this will give you secant x. So this all differentiates to secant theta, and sine becomes cosine. Then y is equal to cos theta. So that's minus sine theta there. Now we need to square them. For this I'm going to manipulate this a little bit because secant is 1 over cos. So if I combine those by doing this, then we get 1 minus cos squared in the numerator, and 1 minus cos squared is sine squared theta over cos theta. And actually, let's call that sine theta tan theta. So squaring that is sine squared theta tan squared theta, and dy by d theta squared is sine squared theta. Now adding them together, you might see why that was worth doing. Got that common term. Sine squared theta, tan squared theta, plus sine squared theta. Factorize out sine squared theta, and we get this lovely 1 plus tan squared theta, which is equal to sec squared theta, which is 1 over cos squared, which equals tan squared theta. Oh, that was nice. Especially as we're now going to square root that. So a2 is 2 pi integral of y times the square root of tan squared theta. And that is 0 to pi by 4. Y was cos theta, and this is tan theta, which is sine over cos. So that all cancels down very nicely to give me sine theta d theta from 0 to pi by 4. And that is negative cosine theta. And that, putting in the limits, is negative root 2 over 2 minus negative 1. So it's 2 pi 1 minus root 2 over 2. Now our total surface area, a total is a1 plus a2 plus a3. a1 was pi and a3 was pi by 2. So that's pi plus 2 pi if I expand this bracket at the same time, minus 2 pi root 2 over 2 plus pi by 2 from a3. A little bit of calculator work to make that easier. We get pi 7 minus 2 root 2 over 2. Does that match how they want it? Not quite. No, we want a pi by 2 outside, and then the 2 inside should be integers. So we bring that over 2, and that will work out nicely. Pi by 2, 7 minus 2 root 2. And that is our answer for the area. Lots of work, but a nice 8 marks for question 2. On to question 3. Given that y equals r sec pi by 2, where we've got a limit on that from 0 to 2, show that this is true where p and q are constants, but not necessarily integers, to be determined. Okay, we start with y is equal to r sec x over 2, and the first thing I'm going to do is bring that sec onto the left, and then we can differentiate. And going over to the formula booklet, here, if you remember my little trick, you can add in h to each of these, and these are true for the hyperbolics, but the only thing you've got to remember is that you include a negative on this one. So the differential of sech is negative sech tanh. So here we get negative sech y tanh y times by dy by dx, because we're differentiating with respect to x, and on this side just 1 over 2. Now obviously we don't want all these y's in here, we're trying to prove something with just x's and constants. But we can deal with that because y is equal to r sech x over 2. And if you do sech r sech, then they just cancel out, and we can relate tanh into this as well, because tanh y is equal to 1 minus sech, sorry, tanh squared y is equal to 1 minus sech squared y. Same idea, if we can get a sech y, then we can use y is equal to this, and the sech and the r sech will cancel, but we don't have tanh squared, we've got tanh, so we need to square root that, which is okay because there's a square root in our answer. So here we've got negative sech r sech x over 2 times the square root of 1 minus sech r sech x over 2 squared times dy by dx has to equal 1 over 2. So the sech and the r sech cancel out and we get a negative x over 2 times the root of 1 minus x over 2 squared, x squared over 4, dy by dx is equal to 1 over 2, halves cancel, and we want the x squared without a 4. Looking back up here, yep, q minus x squared. So to get the x squared by itself, we force a quarter out of that. We get 4 minus x squared. And when you square root that factored quarter, you get a half. That's still minus x in front. dy by dx is equal to 1 now. Rearrange this, and we get minus 2 over x times the root of 4 minus x squared. So although it said constants, they did end up as integers, where p is minus 2 and q is 4. That's looking good. That's part A finished. In part B, we've got another function. This is a new function, but there is r sech x over 2. So what we've done in part A might be very useful here. Determine in simplest form the exact value of x for which the derivative is equal to 0. So yes, what we've done in part A we're going to use here in part B. So the function is r tanh of x plus r sech of x over 2. Back to the formula booklet. Unfortunately, r tanh is here as a standard result in the FP3 differentiation section, 1 over 1 minus x squared. So the derivative of this is 1 over 1 minus x squared minus 2 over x root 4 minus x squared from part A. And we're saying, when is this equal to 0? Bring that on the other side. 1 over 1 minus x squared is equal to 2 over x root 4 minus x squared. X root 4 minus x squared is equal to 2 minus 2x squared. And now I'm going to square everything and get a quadratic in x squared. That's minus 8x squared plus 4x to the 4. X squared times 4 minus x squared. That's 4x squared minus x to the 4. This side doesn't change. And then we rearrange and get 5x to the 4 minus 12x squared plus 4 equals 0. See if this factorizes. 5x squared, x squared. Get a 2 and a 2, that should work. So x squared is equal to 2 over 5, or x squared is equal to 2. That gives x is equal to plus or minus the root of 2 over 5, and x is equal to plus or minus root 2, but we had some limitations on x. x has to be between 0 and 1. So x less than or equal to 1, greater than 0, means both the negatives are out, and the plus root 2 is too big. So we're rejecting both of those and also this negative here. So our final solution is root 2 over 5. Does that agree with what we had in the question? Yes, the exact value, singular, not values. So that is making me confident. Final answer, there it is. On to question number 4. Here we have matrix M, where k is a constant. Given that 3 is an eigenvalue of M, determine the possible values of k. Different ways to do this. What I'm going to do is just take that matrix and multiply it and make some equations. So this matrix multiplied by x, y, z must equal 3 lots of x, y, z. That gives us the equation 6x plus ky plus 2z must equal 3x. That doesn't look too friendly, but it also gives us kx plus 5y plus 0z must equal 3y. That's looking better. And 2x plus 0y plus 7z is equal to 3z. So 2x equals minus 4z, x is minus 2z, and this one, k is equal to minus 2y over x. So how do I combine these? I think actually I want to keep this as kx and make y the subject instead. Same down here, let's make z the subject, and then substitute these two expressions into this equation here and get just x's and k's. So 6x minus k squared x over 2 minus x equals 3x. You can see that the x's all cancel out nicely. Don't forget that's a 1 still. That gives us minus 2 minus k squared over 2. K squared equals 4, so k is equal to plus or minus 2. 2 values? Yes, plural. 2 values is okay. Given that k is less than 0, determine the other eigenvalues of m. Okay, we found it was either plus or minus 2. Now we're saying k is less than 0, therefore k must equal minus 2. So my previous matrix that was that now looks like this. We're trying to find the other two eigenvalues, so we want the determinant of m minus lambda I equals 0. Manipulate this, 6 minus lambda, 5 minus lambda, and 7 minus lambda, and it's the determinant. So that gives us 6 minus lambda times by 5 minus lambda times 7 minus lambda minus 0 times 0 minus minus 2 times by minus 2 times 7 minus lambda minus 0 times 2 plus 2 times 0 minus 2 times 5 minus lambda. I feel like there are a lot of negatives in here. Writing that out, 6 minus lambda. I'll expand this bracket here, 35 minus 12 lambda plus lambda squared, and then I'll expand all of this together, that's minus 28 plus 4 lambda, and then all of this, minus 20 plus another 4 lambda, and all of that has to equal 0. 210 minus 72 lambda plus lambda squared, minus 35 lambda plus 12 lambda squared minus lambda cubed minus 48 plus 8 lambda equals 0. Don't like having a negative lambda cubed, so I'll take it all on the other side and simplify. Lambda cubed. I can see I've missed a 6 in there just as I'm starting to simplify. So that gives me 18 lambda squared, but bringing it across is minus 18 lambda squared plus 99 lambda minus 162 equals 0, and we know one of them should be, what was it, a 3? So form ourselves a quadratic here. A must be a 1, C must be a 54 to get the constants right, and then if I get minus 3a lambda squared plus b lambda squared must equal minus 18 lambda squareds, and we know a is a 1, then b must be minus 15. So lambda minus 3 lambda squared minus 15 lambda plus 54 gives us a 9 and a 6. And of course, minus 3. So lambda equals 3, 9, 6, 9 and 6, the two new ones. That's part B. Part C, determine a normalized eigenvector corresponding to the eigenvalue 3. Now 3 is the one that we already knew, so you could do part C without getting part B. So we're going to do this same thing here, except now we know what k is, and work out an eigenvector. So I'll take that down with me, except that k is minus 2. So we've got 6x minus 2y plus 2z equals 3x. 3x minus 2y plus 2z must equal 0. We've also got minus 2x plus 5y plus 0z equals 3y. Minus 2x plus 2y equals 0, so x must equal y. And 2x plus 0y plus 7z equals 3z. We did have all this information further up. We could have just put minus 2 in for k in the expressions we already had. That's minus 4z, 2x. So if I put everything in terms of x again, we get z is equal to minus x over 2. So we've got all the relationships there. If we let x equal 2, then y is also equal to, and z is equal to minus 1. So we've got 2, 2, minus 1, but that's not yet normalized. We need to find the magnitude, and that is the root of 9, 3. So our normalized eigenvector is 2/3, 2/3 minus 1/3. Final answer for question 4. On to question number 5. Very simple question. Determine these. Okay, to start with, we'll try and complete the square. Get 3 over 2 there. I have to take off the 9 over 4 and still add the 5, which gives x minus 3 over 2 squared plus 11 over 4. So if we want to integrate 1 over the square root of x squared minus 3x plus 5, we can rewrite that as 1 over the square root of x minus 3 over 2 squared plus 11 over 4. And then jump to the formula booklet. Here it is. We've got the root of x squared plus a squared, and that gives us r sinh x over a. So this is equal to r sinh x, which is x minus 3 over 2 in this case, over a, which is root of 11 over 4, or the square root of 11 over 2, plus c on there. And then the 2 in the denominator can come up, and that can simplify to r sinh 2x minus 3 over root 11, if you don't mind a square root in the denominator. Part 2, 63 plus 4x minus 4x squared. This is the thing we're going to now try to complete the square on. For me, what I would do here is take out the negative to give this. Then using that, we can write that as 2x minus 1 squared. And then we have to take off a 1 to make that true. So if we do 63 minus 1, we get 64 minus 2x minus 1 squared, which of course is 8 squared minus 2x minus 1 squared. So the integral of 1 over the square root of that, 63 plus 4x minus 4x squared is the same as the integral of 1 over the square root of 8 squared minus 2x minus 1 squared. And back to the formula booklet. This time we want a squared minus x squared, so it's arc sine x over a. So that becomes arc sine of 2x minus 1 over a, which is 8, plus c, but because it's not x, it's a 2x. When you differentiate that, remembering that the a is slightly separate, we will be multiplying by a 2, so in order to cancel that out we need to multiply by a half here. And that's the end of question 5. On to question number 6. Here we've got an integral for in, and we need to show that this beastly expression is true for n is greater than or equal to 2. 6 marks. And then we're going to apply it for part B. Okay, I feel like there's a lot of algebra about to happen. Integral e to the x sine nx dx, and in this case the integration by parts formula will help. uv prime is equal to uv minus the integral vu prime, and the one we definitely want to be differentiating is the sine to the nx. We don't want to be integrating that, so let's make e to the x v prime and sine to the power nx u. So v is obviously e to the x, and u prime is n times sine to the n minus 1 x times by cosine x. This is going to get messy before it gets better. So we've got u, which is just sine to the nx, times v, which is e to the x, minus the integral of e to the x times u prime, which was n sine to the n minus 1 x times cos x dx. Now we need to integrate this, and what we're going to do is apply the integration by parts formula again, and I'll take the n outside the integral. Let's do that now. And then the e to the x is still going to be our v prime, and we're going to consider all of this to be our u, because we can differentiate that using the product rule. Now our v is still e to the x, but our u prime is more complicated. Differentiate the sine to the nx, we get n minus 1 sine to the n minus 2x times by another cosine x, and then we leave the cosine x from the original expression alone, so that becomes cos squared x. Then we leave the sine to the n minus 1x alone, and we differentiate the cos x, and differentiating cos gives us negative sine. But when we multiply those two together, we get sine to the nx again. So I'll just simplify that here before we put it in. Actually, I'll do some more simplifying here, because although it might not look like simplifying, we don't want that cos squared. Instead of that, we want 1 minus sine squared. Do all of this before we put it into the integral. So that's n minus 1 lots of sine to the n minus 2x when you multiply it by the 1 here, and then minus n minus 1 lots of sine to the n minus 2 times sine squared. That brings us back to sine to the nx, and we're still minusing sine to the nx. Expand out one of those brackets. I'll leave this one for now, but this one I want minus n lots of sine to the nx plus sine to the nx minus sine to the nx. Excellent, that has cancelled down a little bit more. So we've got this expression and this one, which is great because both of those are very similar to what we started with, and we might be able to replace those with in and in minus 2. So all of that work was differentiating u from this expression here in order to put it back into the integration by parts formula. So from our line up here, this is in equals, and we've still got that e to the x sine to the nx term in front, and then we've got minus n lots of, then the integration by parts formula on this integration here is u times v. So our v is e to the x, and our u is sine n minus 1 x times cos x minus the integral of vu prime. Now v is still e to the x, but u prime is now this quite nicely simplified expression, n minus 1 sine n minus 2 x minus n sine n x dx. So I'll expand the big square brackets with the n factor in front, and I will also split that integration into two integrals. So all of this is e to the x sine to the n x minus n lots of e to the x sine to the n minus 1 x cos x, minus times the minus in front gives us a plus n, and I'll bring this n minus 1 bracket outside as well, integral e to the x sine n minus 2x, and then we've got three negatives compounding here, so we've got a minus n from in front of the square brackets here, and this n here, so that's n squared times the integral of, missing brackets, there's brackets all over the place, that e to the x is in front of both of these. So we've got e to the x sine to the nx. Now that's pretty horrible looking, but we can now replace the two integrals with I n minus 2 and I n. This is minus n squared, lots of that, and this is plus n minus 1 of these. And then let's have a look at what we need. We want a sine x minus n cos x in brackets and the sine to the n minus 1 in front. So we can pull a sine n to the minus 1 with an e to the x. And what we've done there is we've pulled most of these sine to the nx bits into here, but there's still a sine x left over. And we've pulled all of these out, so there's no sine x here at all. That's why we get a sine x minus n from here, n lots of cos x in that bracket there. And then all of this is still equal to I to the n, so we're going to bring this term onto the left. So we've got I to the n 1 plus n squared when you factorize out I to the n, and all of that still equals e to the x sine n minus 1 x sine x minus n cos x plus n minus 1 lots of I n minus 2. Then divide everything through, and hopefully this matches what we needed. That's over 1 plus n squared sine x minus n cos x plus n minus 1 over 1 plus n squared I n minus 2. Yes. So I think by far the worst part of that was this mess of algebra here and working that through these three lines here. But that's our expression that we needed. And now in part B we need to use it when n is equal to 4 and we're going from 0 to pi by 2. So we've got I4 and we're just applying that to the expression at the top of the screen there. So that's e to the x sine cubed x over 1 plus 4 squared. 4 squared is 16, so that's 17 times sine x minus 4 cos x, and all of that needs to be evaluated at 0 pi by, what was it, 2 plus 4 minus 1, 3, 1 over 4 squared, 17 again, 4 minus 2 is 2. So just reading along this expression here, putting in n equals 4 gives me this. Fortunately, sine of pi by 2 gives me 1, cos of pi by 2 gives me 0, sine of 0 gives me 0, and cos of 0 gives me 1. So a lot of things in there will simplify. E to the pi by 2 times 1 over 17 times by 1 minus 0 minus e to the 0 times the sine cubed of 0, so everything there after that is going to be 0. So that is a nice easy expression coming out of those limits. But we still have this second term, so we've got plus 12 over 17 lots of I2. Now we have to apply the expression again with I2. So that's e to the pi by 2 over 17 plus 12 over 17 lots of, now again this expression up here on the previous page with n equals 2, e to the x sine of 2 minus 1 x over 1 plus 2 squared, that's 5, sine x minus 2 cos x, and again this is being applied at 0 pi by 2 plus n, which is 2 times n minus 1 over 1 plus 2 squared, I to the 2 minus 2 is 0. And that's where we'll have to do an actual integration. But I do have to close that bracket because that's also being multiplied by 12 over 17. So that's e to the pi by 2 over 17 plus 12 over 85 e to the pi by 2, and then the sine x is a 1, sine x is a 1, 2 cos x is 0, so there's nothing else there on that term. And then when we apply the 0 limit, sine 0 is 0, so it's completely gone, so there's a minus 0 there if you want. And then we've got 12 over 17 times the 2 over 5 here, that's plus 24 over 85 I naught, and I naught is the integral from 0 to pi by 2 of the original integral here, with n equals 0, so sine to the 0 is a 1, so it's just e to the x. So we've got e to the x dx. The two first terms add together to give a surprisingly nice pi by 2 over 5 there, and then 24 over 85 e to the x with the limits of 0 to pi by 2, so e to the pi by 2 over 5 plus 24 over 85 lots of e to the pi by 2 minus e to the 0. Expanding and collecting gives us 41 over 85 lots of e to the pi by 2 minus 24 over 85. Wow, I don't know about you, but that felt like it was hard-earned marks. So that was part B. Where did part B start? There. And that's the final answer. Moving on to question number 7. The line L has equation this. Don't like that. Let me quickly put it into column vectors. 3, 5, 4 plus lambda 4 minus 2, 7. The plane pi has equation this, and that is r dot 2, 4 minus 1 equals 1. The line L intersects the plane pi at the point P. Determine the coordinates of P. Okay, so we need the two to be put together. So from my line equation, r is equal to 3 plus 4 lambda, 5 minus 2 lambda, and 4 plus 7 lambda. And that has to go into the plane equation. So we're going to dot that with, get rid of that, 2, 4 minus 1, and that has to equal 1. So 2 lots of 3 plus 4 lambda, plus 4 lots of 5 minus 2 lambda, minus 1 lot of 4 plus 7 lambda equals 1. 6 plus 8 lambda, plus 20 minus 8 lambda, they're gone. Minus 4 minus 7 lambda equals 1. So 7 lambda is equal to 21, and lambda is a nice round 3. But that's not the coordinates of P. What we need to do now is put that back in to our equation. 3 plus 4 times lambda, which is 3. 5 minus 2 times lambda, and 4 plus 7 times lambda. 15 minus 1, 25. And that's the position vector that will get us to P, so the coordinates of P, 15 minus 1, 25, like so. The acute angle between L1 and pi is theta degrees, determined to 1 decimal place the value of theta. So we've got ourselves a plane. The line is coming through like this. Here we've got theta, and of course our normal n is what's going to help us here, but it will help us find this angle. So we've got L1 here, and P is here. So to find, let me call this alpha, to find alpha we can do L dot n, and that equals the magnitude of L times the magnitude of n. Oh, when I say L, what I mean really is the direction vector of L times the cosine of the angle between them. This is part B, and the direction vector of L is 4 minus 2, 7. And the normal is 2, 4, minus 1 for the plane. So 4 minus 2, 7 dot 2, 4 minus 1 must equal 4 squared plus 2 squared plus 7 squared square root times 2 squared plus 4 squared plus 1 squared square root times cosine of alpha. 2 times 4 is 8, minus 2 times 4 is minus 8, and then 7 times minus 1. This is the square root of 69, square root of 21. So cos alpha is equal to minus 7 over the square root of 1449. So alpha is 100.596 dot dot dot. Now that might seem weird because of how I've drawn the diagram. Alpha is clearly less than 90 degrees on my diagram. What that means is my direction vector isn't actually going out like this. It's going into the plane like this in terms of how I've drawn it. So what that 100 degrees is doing is not this small angle, but this angle here. So to get alpha, I do 180 minus the angle I just found, or to get theta directly, I can do the angle I've just found minus 90. So have a diagram, but be aware that we weren't entirely sure which direction that direction vector was going along the line, and that will have an effect as to exactly which angle you're finding. So in this case, theta is equal to, sorry, let me change, alpha on the diagram is this slightly large angle this way. So theta is alpha minus 90 in this case. And that is 10.6 degrees to 1 decimal place. That is part B finished. The line L2 lies in pi and passes through P. We don't have L2 up there. So it lies in pi and passes through P. Given that the acute angle between L1 and L2 is also theta degrees, determine a vector equation for L2. So what that means is, although L2 lying in the plane doesn't really give us much to go on, it could be in any direction in the plane, and passing through P doesn't give us much to go on either, it could still be in any direction in the plane. Knowing that the angle must also be theta puts it along the dotted line I've already drawn. It must be going along this direction here, in the plane, going through P. That's the only line that will give me an acute angle theta. Another way to say that is, if I draw on L2, L2, L1 and N all happen in the same plane, a plane perpendicular to the plane I've got drawn on the diagram. To find the normal to that plane, I want it to be perpendicular to N and L1. So I can just cross the direction vector, actually these two here that I've got on the screen already, the direction vector of L1 and the normal to the plane. That will give me a perpendicular direction vector to both, and that will give me the normal to this second plane that I'm not going to try and draw. But once I know the normal to the second plane, to get the direction vector of L2, which is effectively the line of intersection of the two planes, I can cross the two normal vectors. And all of this has come from the fact that L1 and L2 must be in the same vertical plane, because otherwise the angle theta would not be the angle between them. Thinking all that through is kind of where the hard work is. What we actually need to do now is just B cross N, and then take that answer and cross it with N again, and then use P as our point for the line. I hope that made sense. So we're going to do b cross n, which is 4 minus 2, 7, cross 2, 4 minus 1, to minus 28, 14, minus minus 4, 16 minus minus 4. Get minus 26, 18, 20. And remember, this is a direction, so if we want to simplify that to minus 13, 9, 10, we can. So this is the normal to the plane that contains L1, L2, and n. Now we want to do the cross product between the two normals to find the direction vector of the line of intersection, which is L2. So we're crossing that with 4, 2, minus 1, minus 9, minus 40, 20, minus 13, and minus 52, minus 18. That is minus 49, 7, and minus 70. Oh, that's quite nice. Because again, this is a direction, so we can simplify that, divide them all by 7, or minus 7 even. We get 7 minus 1, 10, as the direction of the line. So this is kind of my B direction vector for this L2, but it also goes through P, and we found the coordinates of P somewhere. There they are, 15 minus 1, 25. So 15 minus 1, 25 is the point, plus some multiple of that direction vector is the line equation for L2. If you could see that that was what you needed to do, the actual process there wasn't too bad. Moving on to the last question, question number 8. The ellipse E has equation this. Determine the eccentricity of E. From the equation, we know A equals 3 and B equals 2. We also know, or it's in the formula booklet if you need a reminder, that this relationship is true for an ellipse. It gives us 4, 9, 1 minus e squared. 4 over 9 is equal to 1 minus e squared, so e squared is equal to 5 over 9, and e must be positive because it's between 0 and 1, so root 5 over 3. That was fairly easy for the last question. Part B. Hence, for this ellipse, determine the coordinates of the foci and the equations of the directrices. That's also fairly straightforward. And also in the formula booklet. Plus and minus AE0 for the foci. So we get plus and minus, we know A is 3 and E is root 5 over 3. So we get plus minus root 5, 0. And the directrices, x is equal to plus or minus A over E. So x equals plus or minus 9 over root 5, or 9 root 5 over 5. Not a bad start to the question at all. The point P lies on E and has coordinates this. The line L1 is tangent to E at the point P. Using calculus, show that an equation for L1 is this. So starting with the equation, x squared over 9 plus y squared over 4 equals 1. Differentiate. 2y over 4 dy by dx equals 0. Rearrange. Dy by dx is equal to minus 2x over 9 times 2 over y, giving minus 4x over 9y. But we've also been given the point 3 cos theta 2 sine theta. So we can put that in. So our gradient of a tangent is minus 4 times 3 cos theta over 9 times 2 sine of theta, giving minus 2 cos theta over 3 sine theta. Now if we put that into our usual line equation, y minus y1 equals mx minus x1, y minus 2 sine theta is equal to minus 2 cos theta over 3 sine theta, x minus 3 cos theta, and then how do they want it to look? x's, y's, and a constant on the right. So multiply everything by 3 sine theta, 3y sine theta minus 6 sine squared theta. Expand the brackets, minus 2x cos theta plus 6 cos squared theta, 3y sine theta plus 2x cos theta is equal to 6 lots of cos squared theta plus sine squared theta, which of course is a 1. Change the order here to match what they've got, and we are finished. Part D. The line L2 passes through the origin and is perpendicular to L1. The line L1 intersects the line L2 at the point Q. Determine the coordinates of Q. So we're going to use the perpendicularity and then set the two equations equal to one another. So it's perpendicular to, so we're taking this gradient here and doing m1, m2 equals minus 1. So if that is m1 on the screen, m2 is 3 sine theta over 2 cos theta, and we know it passes through the origin, so y minus 0 equals mx minus 0. So there it is. That's L2. Now we want to know where L2 and L1 intersect. So the equation here for L1, equation here for L2, put them together. So I'll substitute in 2x cos theta plus 3 lots of y from the other equation, 3 sine theta x over 2 cos theta. Back to the first equation, sine theta equals 6. Times everything by 2 cos theta, 4x cos squared theta, 9 sine squared theta x is equal to 12 cos theta. Now my mind immediately says, oh, solve a quadratic in cos theta, but that's not what we're doing. We're trying to find the x coordinate. So we just factorize out x, and although it's fairly horrible looking, we then divide through by that, and that gives us an awful looking x coordinate. But that is it. And then we want the y coordinate as well. So on the screen at the top there, y is equal to 3 sine theta over 2 cos theta times x, which is this horrible thing. 4 cos squared theta plus 9 sine squared theta, and then that can cancel a little bit, and we get a similar but slightly different 18 sine theta over the same denominator for y. So the coordinates of, I think it was Q, are 12 cos theta over 4 cos squared theta plus 9 sine squared theta, 18 sine theta over the same thing. Okay, not quite so nice, that part, but not too bad. Final part, show that as theta varies, the point Q lies on the curve with equation this, where alpha and beta are constants to be determined. 3 marks. Okay, that doesn't look like a very nice. We've got x squared plus y squared squared, but the approach is fairly standard. What we should be doing here is letting the x coordinate we found be capital X. Oh, the number of times I've written this denominator. And capital Y be the y coordinate that we found. And then we're trying to combine them into one equation. And usually what I would look to do here is to square them, and then you get a cos squared and a sine squared, you rearrange and you make cos squared plus sine squared equals 1. But because of this horrible looking denominator, that's not going to work. In this case, it's not at all obvious what you should do, unless you've seen something similar before. But what I'm going to do is take the x-coordinate and I'm going to divide top and bottom by cos squared. So you have 12 cos theta divided by cos squared theta. And then here, 4 cos squared theta over cos squared theta plus 9 sine squared theta over cos squared theta. What that does is give me 12 secant theta in the numerator and 4 plus 9 tan squared theta in the denominator. And why that's useful is because we can connect secant and tangent through an identity, but more importantly, because the x and y coordinates have the same denominator, we can get a tan theta by dividing them through. So if I do y divided by x, we get 18 sine theta with the denominator divided by 12 cos theta with the same denominator. The denominators cancel and we get 18 sine theta over 12 cosine theta, which of course is 3 over 2 tan theta. Now we can substitute that by rearranging. Tan theta is equal to 2y over 3x. And we can also substitute it into secant using that connection through their identity. And that will allow us to get this expression in a couple of different forms into this expression, connecting it with x over here in a formula that will just have x's and y's. That'll be fairly messy, but we knew it was going to be fairly messy. So tan squared theta from here is the same as 4y squared over 9x squared. And we know that secant theta is equal to, because sec squared is equal to 1 plus tan squared, is equal to the square root of 1 plus tan squared theta. And putting that in here, that's the same as 1 plus 4y squared over 9x squared. Now that's a lot of work, but we're going to put this expression and this expression into here. And we know that the left-hand side is still x equals. So 12 times secant theta, which is the root of 1 plus 4y squared over 9x squared, over 4 plus 9 tan squared, which is 4y squared over 9x squared. And this is our expression relating x and y. The only thing left to do is to make it look like they want it to look like. So I'll take the denominator up on the left, and that gives us a 4x plus 9x, lots of 4y squared over 9x squared, so that cancels, and that with one of those. 12 root 1 plus 4y squared over 9x squared, times everything by x to get rid of that fraction. We get 4x squared plus 4y squared is equal to 12x root 1 plus 4y squared over 9x squared. Now if I edit this a little bit, save some lines of working, that factorizes and then we can cancel that, gives us a 3, and then I square everything to get rid of the square root. And that gives us this awkward x squared plus y squared squared, which isn't very nice, but we know that we need in our expression from the question 9x squared 1 plus 4y squared over 9x squared. Multiplying that out, we get 9x squared plus 4y squared. And I think that matches all the way back. Yes. So alpha and beta are 9 and 4. And that finishes off the paper. Although I feel like those last 3 marks were very hard earned. If you got that one, very well done. I hope that has been of some help for you.